All right, friends, TLDR, infinite series. An infinite series is just an infinite sum that, when you add together, equals a finite value. So essentially, it's a sequence, but instead of just listing the terms, you're adding together the terms of the sequence to get the series. And the series will sometimes equal a value, and if it does, we say it converges to that value. Other times, it will not equal a value, and then we say it diverges. So an infinite series can do one of two things. It can converge to a value, or it can diverge. In this section, we're pretty much just determining if it converges or diverges. Now, if you notice this series right here, in the longer version, I showed you how I got through all this. It's kind of important, but really, long and short, here's an infinite series. 0.3 plus 0.03 plus 0.03, 0.003 plus 0.0003. I can write this using what's called sigma notation. The bottom number tells you what to start plugging in. The top number tells you what to stop with. So in this case, you plug in 1, and you get this first term. Plug in 2, you get this next term. Plug in 3, you get this next term. Technically, I should have done 4 and 5, but I cut it off early. And then you would add those together, and that's called a finite series. But we're not going to be dealing with finite series in this class. We're going to be dealing with infinite series, where the top bound is infinity, meaning you're going to get an infinite sum. But remember, an infinite sum can actually equal a value. In this case, this infinite series equals 1/3. And part of this is going to be sometimes determining what in fact it converges to. So an infinite sum that equals a finite value is the same as saying what that infinite sum converges to. So infinite sum, when it equals something, that means the infinite series converges to that value. Okay, two very important examples. These are both infinite series. Notice the top bound is infinity. And one thing we can do when we start to analyze whether they converge or diverge is called expanding it out, where we write out all of the terms. So if you plug in 1, you get a half. You plug in 2, you get a fourth. You plug in 3, you get an eighth. Plus, plus, on and on and on to infinity. The very key thing here is to look at what this series is doing and notice that the terms are getting smaller and smaller and smaller. That plays a role today for sure. So rather than dive into how to do this, I wanted you to analyze something first called finding the partial sums. Partial sums is just saying, okay, look at the sum of the first term. You get 1/2. Look at the sum of the next 2 terms. That's the second partial sum. You would get 3/4. Find the sum of the next 3 or the first 3 terms. That's called the third partial sum. It's 7/8. Find the sum of the 4 first terms or the fourth partial sum. That's 15/16. And you can start to look at the what these partial sums get closer and closer to. In other words, if these partial sums approach a value, it looks like they're getting closer to 1. That means that the series, in fact, converges to 1. That is one way to kind of wrap your mind around what you think is happening. That's not a formal proof. That's just showing, oh, look, it looks like if I found the partial sums, that I'm getting closer and closer and closer to 1. Whereas on the flip side, if we have this series and we expanded it out, the first partial sum would be 2. The second partial sum would be 6. The third partial sum is 14. The fifth partial sum is 30. Look, these partial sums are getting bigger and bigger and bigger, which means that this infinite series likely diverges. And it does, for reasons we'll talk about in a second. So I then did this first major example. This is a very, very, very key example to understanding the whole process. So we have an infinite series, k equals 1 to infinity. So I started by expanding out the series. And I got 4/3 plus 7/4 plus 10/5 plus 13/16. Ignore this for right now. And I say, okay, rather than list the partial sums, let's just look and see if we can look at the sequence and see what the sequence is doing. Well, from last section, we saw that we can look at the end behavior, and we see that the sequence is converging to 3. In other words, this sequence's quote unquote last term is 3, and every number before it is very close to 3. So really what this sequence is, it's kind of like you're just adding 3 over and over and over again, essentially. Because these last terms, the infinite terms, are just getting closer and closer and closer to 3. So if the sequence converges to 3, that means the last term is 3. That means we just keep adding 3. Our series is never getting closer to a value because we keep adding 3 every time we take the series further and farther, which means the series diverges. Now, this process is called the test for divergence, also known as the nth term test. It's where you look at what the sequence is doing, and based on what the sequence is doing, you have an idea of what the series is going to do. So then I went into 3 examples. Here's the first one. What does this series converge to or diverge? Well, we're not going to find what converges to today. Instead, all we're asking the question of, does it converge or diverge? So instead, we're going to look at the sequence. Based on last section, we know that this sequence diverges because the growth rate of the top is way bigger than the bottom because factorials grow faster than exponentials. So because the sequence diverges, the series definitely diverges by what's called the test for divergence. If the sequence diverges, the series diverges. Perfect, done. Notice right here, it didn't equal 0. I'll talk about that in a second. How about the second example? Well, same logic. I can do the test for divergence, which means look at the sequence. The sequence equaled 5/3. How nice. The sequence converged to 5/3. But what does that mean for the series? That means the series diverged because you're just adding terms that are getting closer and closer to 5/3, which means you're never getting a sum that's approaching a value. So in other words, this series just diverges again because we didn't get 0, and that's what I said here. So obviously in the last case, we have cosine n over n squared. Remember, when we're dealing with cosines and sines, you can replace them with 1 for now. Really, they do the same thing because cosine and sine don't grow. They fluctuate. So they're pretty much similar to 1 at infinity. So what is this series doing? Well, if you notice, if I expand it out, we're getting closer and closer and closer, term for term for term, to 0, which means the end behavior of this series based on the, or of this sequence based on the last section is 0. So immediately students will be like, well, that means it's convergence and we're done. If that was how this worked, this would be a joke of a section because this is all we'd ever have to do. It's not that simple. There's no conclusion in this case. We don't know what this series does. We have to use another test, which is coming later. So you cannot say, and I say never say, a series converges by the test for divergence. That is an awful, awful, awful thing to say because the test for divergence only proves divergence. It does not prove convergence. We have to do another test. So if you use a test for divergence and you get that the sequence converges to 0, no conclusion, we have to do another test. So essentially we wouldn't even use this test, but we haven't learned any other tests yet. So the homework tonight's not bad. You're basically going to get either the sequence converges to a number or diverges, and that is both those cases, the series diverges, or you're going to get 0, which means the test is inconclusive. Okay. And that is essentially what's going on in this section. All right, that's it.